Okay, this is a lesson on vectors. Vectors have magnitude, which is a number or scalar associated with them, as well as direction. So they're mathematical objects that can be represented by arrows. Okay, so here's an example. I'm writing vector v, note the notation, and it's written with these kind of cornered brackets right here. So this is the vector 2, 3, those are the components. And it can be represented with an arrow, which is a directed line segment. So here's an example, a picture of my vector v, where the first component is 2 and the second component is 3. I go over 2 and up 3. And my tail of my vector is at the origin, and the head of the vector, that's where the arrow is at the point 2, 3. So the point 2,3 is different than the vector 2,3. The vector is the entire arrow. And this vector is in standard position because its tail is sitting at the origin. So please make a mental note of this notation. If you have just a segment there without the arrow, then you do not have a vector. Okay, so again, this is the tail, right? And this is your head of your vector, tail, head. Okay, so the vector up here is in standard form because the tail is sitting at the origin. But that's equivalent to all of these other vectors that are going in the same direction with the same magnitude. So there's an infinite number of vectors. We say they're all isomorphic. They all are going over 2 and up 3 from tail to head. You can see that they all look parallel to each other. And they're all going at the same angle to the horizontal. Okay, but this is the only vector here that's in standard position because the tail is sitting at the origin. Okay, then we can talk about the magnitude of a vector. It kind of looks like the absolute value symbol. Sometimes you see it with a double bar, sometimes you only see it with a single bar. And this is the scalar that's associated with the vector. And you can calculate it just with the Pythagorean theorem. So it's essentially the length of that arrow. So the magnitude of v, okay, the length of the arrow, magnitude of vector 2, 3, and you're looking at basically the hypotenuse in that right triangle. So square root of 2 squared plus 3 squared. So the magnitude of v is root 13. We can also talk about the angle, and it's just the way you think about trig angles in standard form, right? It's the angle made with that positive x-axis. Using arctangent is nice because you only need the two components to be able to do that. It would be arctangent of 3 over 2, which your calculator can tell you is 56.3 degrees about. Okay. So in general, if I have vector v with components a, b, its magnitude is, use the Pythagorean theorem, the square root of a squared plus b squared. And to find the direction, the easiest way is with arctangent. Please be very, very careful. Sometimes you have to use the calculator's answer, right, which is the principal value between negative 90 degrees and 90 degrees to figure out the direction. Let's try an example with that. So find the magnitude and direction of vector v, components negative 4 and negative 12. Pause the video and try it. Okay, so you have to think about the quadrant, right? The quadrant here is really terminating in the third quadrant. Your calculator is not going to tell you the angle for a third quadrant terminating vector. So you have to use the calculator's answer. When you do arctangent of negative 12 over negative 4, right, and here's the picture, right, so negative 4 over and then down 12, do arctangent, you're going to end up with a positive 71.56. That's really just the reference angle right here, and you're adding that to 180. So your angle in this is 251.57 degrees. Your magnitude, Pythagorean theorem with your two components, right? The length of this hypotenuse right here is the length of your arrow. It's the square root of 160. Don't leave it that way. You guys should know to leave it in simple radical form. Okay, so reminder, okay, tail of the vector, head of the vector, right? When we write the vector 2, 3, we're using these cornered brackets right here, and it's different than the actual point 2, 3. These are the coordinates of just the head of the vector, okay? And that's when it's in standard form. It would be the coordinates of the head of the vector. This vector is not a point, okay? It is a vector. Okay, so I want you to try this. I want you to find vectors, another way to write it, AB. Okay. If the tail of AB is at A, and I wrote A first, that's what that means, the tail is at A. And the head of vector AB is at B, which is at -1, 5. Draw yourself a picture, pause, and try that. You're trying to find vector AB. Okay, you should have a picture that looks like this. Okay, so there's your picture of vector AB, tail at A, head at B, and you're looking to see how much over and how much up you have to go from A to B. But you should realize that what you're actually calculating, because these numbers could be big, you're not going to want to draw the picture every time, is you're taking the coordinate -1 minus -3 to figure out that this is 2, and you're taking 5 minus 2 to get 3 here. So you're taking head coordinates minus tail coordinates to actually figure out your vector. Be careful, that order matters. You're taking head coordinates minus tail coordinates. Take a moment to write that down. Head coordinates minus tail coordinates to get the vector 2, 3. Okay, if the signs of either one of these are incorrect, like you had one of them negative, you got that wrong, and that's a source of many, many mistakes that people make. So note that vector AB is in the opposite direction of vector BA. If I drew them, it would look like this. Here's vector AB, here's vector BA. Very, very different, okay, pointing in different directions. Okay. If you don't have an arrow, then you don't have a vector. So if all you did was make little segments here, then you did it wrong. Okay, let's talk about scalar multiplication. Scalar multiplication is when you take a vector and you multiply by some number. So k times vector xy, I can multiply that k in and I get kx, ky. Here is an example with that. So if I take the vector 2, 4 and I multiply by -3, I'm getting a vector in the opposite direction of vector 2, 4 that's 3 times as long as my original vector. So here it is. Okay. Let's also talk about unit vectors. Michael, I'm recording. Okay. Let's talk about unit vectors. Unit vectors are vectors of length 1. How would you find a unit vector in the direction of 2, 3? Take a moment and think about it. These are vectors of length 1 in the same direction now as the vector 2, 3. Unit vectors in general are vectors of length 1. I want you to find a vector that's in the same direction as vector 2, 3, but only has length 1. This one has length √13. Okay. One way to do it is to think about similar triangles. So here's the vector 2, 3 at an angle theta. And so here's the √13. This is 2, 3, really exaggerated picture. And I only want it to have length 1. So I know I have to go over an amount A and up an amount B here. So there's some similar triangles. There's similar triangles in my picture, like A over 2 equals B over 3. There's one relationship. But it's also true that A squared plus B squared is equal to 1. So between these two relationships right here, you could solve for A and solve for B. That's kind of the harder way. Another way to do this, reveal the easier way, is you take your vector v, okay, and you just divide by its length, right? So you shrink it down to a vector that has length 1 by dividing by its length. So I divide the vector by √13, right? Essentially taking each of the components and dividing them by √13. I want you to note the little hat that's sitting over the v. This is our notation for a unit vector. So this is a unit vector in the direction of v. This vector has length 1. If I do this squared plus this squared square root, I'm going to get 1. Okay. So in general, if w is the vector xy and I want a unit vector, note the notation, w hat, I take xy and I divide by square root of x squared plus y squared to each of the components. So I want you to try this. I want you to find a vector that is 5 units long, but in the direction of -1, 3. Pause the video. Okay, so a vector in the opposite direction would be 1, -3, right? But now what I'm going to do is I'm going to shrink it down to a unit vector by dividing by its magnitude, which is √10. Now this vector is only 1 unit long, and I can make it as long as I want by multiplying by anything I want. I want to make it 5 units long, so I'm going to multiply through by 5. And what I end up with is right here. So I could have made that vector any length I want, and it's in the direction, the same direction, or in this case, in the opposite direction of this vector. Okay, there are special unit vectors. So unit vectors I and j. I is the vector 1, 0, and j is the vector 0, 1. So notice again the little hat over the I and the little hat over the j. You will see sometimes vector uses this component in this notation, which I'm going to explain in a minute. So now we can talk about, you now know enough to talk about vector addition. If I have two vectors, v and w, where the components are v1, v2, w1, w2, adding them, you probably would guess how to add them. You add the two horizontal components and you add the two vertical components. And what you end up with is v1 plus w1, v2 plus w2 for your components. Geometrically, it makes sense. Let's look at y. If this is my vector v, then here is v1 and here is v2. And if this is my vector w, here is w1 and here is w2. My resultant is the vector that I get when I start at the tail of v and go to the head of w. So this is called the head to tail method. When I'm adding them, I'm putting the vector w, the tail of vector w, at the head of vector v. Okay, this is vector v first, tail of w is at the head of vector v, so this is v plus w. And when I add them, the resultant starts at the tail of the first one and ends at the head of the second one. So this is the resultant. This is the sum of those vectors. Okay, and you can see that it's got components v1 plus w1, v1 plus w1 to get here, and then v2 plus w2 to get here. So this is the resultant. This is called the head to tail method, where I take the second vector plus the first using head to tail. Okay. There is another method, which is the parallelogram law. You'll use it less, but it's still kind of important to know. So instead of doing the head to tail method, where I've got here's vector v and w is at the head of vector v, instead I'm going to move w and v tail to tail. So let's say here's my vector w. Remember, these vectors can move all over the plane parallel to each other. Okay, so this is also equal to vector w. Now vector v and w are tail to tail, and I complete the parallelogram, and the resultant is the diagonal of the parallelogram, where the tail of that resultant again is at the tail of w and v. So this is the resultant. Okay, so these are two ways to geometrically add vectors. You're going to want to know how to do that. And algebraically, you're simply adding corresponding components. Okay, so next question. I want you to write the vector 4, 9 as a linear combination of two unit vectors. Pause the video. Okay, so here it is. 4 times 1, 0 plus 9 times 0, 1. Here's 4, 0, and here's 0, 9 when you multiply through, and that gives you the vector 4, 9. So what you're seeing is that when you do 4 times 1, 0 and 9 times 0, 1, you're actually doing 4i plus 9j, and sometimes you see these vectors are equivalent, same thing. This is just another way to write it, and you see that in physics a lot, where you see the components split up with the horizontal and vertical. That's called a linear combination. Okay, and you can see kind of a picture of that. Okay. Here's 4i, here's 9j, Here it is using the parallelogram law. Okay, and then finally, almost done. Here's vectors. So I want you to draw what the vector calculation would look like if I'm going to do W minus V, if this is W and this is V. Pause the video and try it. I'm going to show you 3 different ways. So one way to do it is here's W. Okay, and I'm going to draw minus V, so I'm going in the opposite direction. So let's see, this is the same length, but in the opposite direction. So what I'm doing, there's no subtraction really. What you're doing when you're doing W minus V is you're taking W and adding the opposite of V. So I'm taking W and adding the opposite of V. The way I'm doing it, tail to tail, I'm going to use the parallelogram law, complete the parallelogram. And so the resultant, more like a parallelogram, the resultant there starts at the tail of both of them and goes along the diagonal. So that's W minus V. Okay, so that's one way, and that's using the parallelogram law. Another way, here's W. Okay, here's V. Okay, so I'm taking minus V, and I'm going to do head to tail method. So I'm going to put minus V starting at the head of W. Minus V is going like that. So here's W plus minus V. So this is the head to tail method. And again, here's the resultant. Okay, these should be the same length right here, and they should be parallel to each other. Okay. So that's the resultant. So that's another way to do it. And then another way to think about it is let's put them tail to tail. So here's W, here's V, and I'm trying to calculate W minus V. So I'm going to call this is probably the way you're most likely going to think about it. I'm going to call W minus V a new vector P. What that means is that when I take V plus P, I get W. So it must mean that when I put a new vector at the head of V and go towards W, I'm going to get W. V plus P is going to equal W. And so this is W minus V. The P is the W minus V. So this is probably the way you guys are going to be thinking about it. Often people get the direction of P incorrect, going in the other direction. But if you just think about this, you write it as W minus V, call it P, and realize you have to add something to V to get to W. V plus this new P gets you by W. You'll get it in the right direction. The last thing I wanted to talk about has to do with displacement. So your packet, your parametrics unit starts right after the polar unit. And in your packet, you have this problem in example number 2. I want you to draw out the final vector, the final position vector of the torus. Take a moment, pause the video. Okay, so what you end up with is going 2 blocks north, right? Remember, you have arrows, not segments. 2 blocks north, 1 block west, 3 blocks south, and 3 blocks east, right? Here's your starting point, here's your ending point. So this is the vector 2, -1. This is called a displacement vector, same thing as a position vector. It's telling you, these are the same. It's telling you your final position with respect to your starting position. Okay, that's also called displacement. So I want you to know that word, displacement and position, same thing. You guys are going to be doing for tonight homework number 1. Okay, so homework number 1 starts on page 4. Don't do problem number 6. Problem number 5 is very important. And then make sure that you get to problems 7, 8, and 9 on page 6.